What is the difference between intrinsic and extrinsic semiconductors? Breaking news in the world of electrical engineering. The question on many minds today is, what really sets intrinsic semiconductors apart from extrinsic semiconductors? As technology advances, understanding these differences is more important than ever. If you are curious about how these materials impact devices you use daily, you are in the right place. Intrinsic semiconductors are pure materials, like silicon and germanium, that have no significant impurities. Their electrical conductivity comes from the electrons and holes created by thermal excitation. At room temperature, a few electrons gain enough energy to move from the valence band to the conduction band. This movement creates free charge carriers, which help conduct electricity. In intrinsic semiconductors, the number of electrons and holes is equal, maintaining electrical neutrality. On the flip side, extrinsic semiconductors are modified by adding impurity atoms, known as dopants. This intentional introduction changes their electrical properties. These dopants can either add extra electrons or create holes, increasing the charge carriers beyond what thermal excitation can provide. There are two main types of extrinsic semiconductors. N-type semiconductors are created by doping with elements that have more valences electrons than the semiconductor itself. For instance, phosphorus is often used in silicon to create N-type semiconductors, where extra electrons become the majority charge carriers. P-type semiconductors, however, are formed by doping with elements that have fewer valences electrons. Boron, when added to silicon, creates holes that act as the majority charge carriers in p-type semiconductors. The key difference lies in the source and concentration of charge carriers. Intrinsic semiconductors depend on the pure material properties and thermal generation of carriers, leading to lower conductivity. In contrast, extrinsic semiconductors exhibit higher conductivity due to the additional charge carriers from the doping process. This ability to control the electrical behavior of semiconductors is vital for designing devices like diodes, transistors, and photodetectors. As the demand for advanced electronic devices continues to rise, understanding these differences becomes essential for engineers and innovators alike. Stay tuned for more updates on this exciting topic in electrical engineering.